Late October 1944, the rain-soaked fields outside Aachen, Germany. Sergeant Harold Becker's M4A1 Sherman took the hit at approximately 400 meters. The 88mm shell from a concealed German anti-tank gun struck the right sponson at a shallow angle, punching through the vertical armor plate and penetrating deep into the hull's interior. The impact threw Becker against the turret wall. His loader collapsed onto the turret basket floor. For 3 seconds that stretched into eternity, the crew waited for the catastrophic secondary explosion that would turn their tank into a funeral pyre. It never came. The penetration had struck directly into the ammunition storage bin, but instead of igniting 40 rounds of 75mm shells in a chain reaction that would have killed everyone aboard, the German projectile had encountered something American ordnance engineers called wet storage, a glycerin and water solution surrounding each propellant case that absorbed thermal energy and prevented sympathetic detonation. Becker's crew evacuated through the hatches, shaken but alive. The Sherman, though disabled, had not burned. German intelligence officers examining the wreck 3 days later, after American forces withdrew from the salient, would document with growing unease that American engineers had solved a problem German tank designers had never adequately addressed: how to prevent ammunition fires from turning penetrating hits into crew deaths. The mathematics of armored warfare had always included a brutal calculation about secondary effects. A shell that penetrated armor but failed to detonate propellant or fuel might disable a tank without killing the crew. A shell that ignited stored ammunition created an inferno that gave crew members seconds at most to escape before temperatures inside the fighting compartment exceeded 1,000 degrees Celsius. German tank crews called it brewing up. American tankers called it cooking off. The terminology varied, but the grim reality remained constant across all armies. Tanks that burned killed their crews with horrifying efficiency. The Sherman tank, designated M4 medium tank in official American nomenclature, entered combat in 1942 with ammunition stored in sponsons along the hull sides. This placement, dictated by internal space constraints and the need to keep ammunition accessible to the loader, positioned propellant cases directly adjacent to vertical armor plates that represented the most likely impact surfaces during combat. German anti-tank guns, firing from prepared defensive positions, typically engaged tanks from the front quarter or direct side aspects. These firing angles meant that penetrating hits frequently struck ammunition storage areas. The result was predictable and devastating. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. British forces operating Shermans in North Africa during 1942 and 43 documented alarmingly high rates of catastrophic ammunition fires following penetrating hits. Reports from the Western Desert campaigns noted that Shermans struck by German 75mm or 88mm anti-tank rounds frequently burned completely within minutes, making crew survival dependent on immediate evacuation before flames blocked escape hatches. The British Army developed a grim nickname for the Sherman that reflected this vulnerability. They called it the Ronson, after a popular cigarette lighter whose advertising slogan promised it lights the first time, every time. American crews developed similar dark humor, though official casualty statistics told a more nuanced story than the nicknames suggested. United States Army Ordnance Department analysts, examining combat loss reports from Tunisia, Sicily, and Italy during 1943, found that approximately 60 to 80% of Sherman tanks struck by armor-piercing rounds subsequently burned. The percentage varied by engagement circumstances, ammunition load, fuel quantity, and crew response time, but the overall pattern was undeniable. The Sherman had a serious vulnerability to post-penetration fires that killed crews even when the initial penetration itself might have been survivable. German tank crews facing Shermans in Italy and later in France recognized this vulnerability and exploited it tactically. Standing orders for panzer units emphasized aiming for hull shots rather than more difficult turret targets, specifically because hull penetrations were more likely to ignite ammunition and guarantee a kill rather than just a mobility hit. German after-action reports from the Italian campaign frequently noted that Shermans, once hit, typically burned completely, eliminating any possibility of recovery and repair. This observation influenced German tactical doctrine, which emphasized achieving first-hit capability through superior optics, crew training, and favorable defensive positioning. If the first shot achieved penetration, the target Sherman would likely burn regardless of whether the crew could theoretically have repaired mechanical damage and continued fighting. The problem was not unique to American tanks. Soviet T-34 tanks stored ammunition throughout the fighting compartment with minimal protection, resulting in catastrophic fire rates that exceeded even the Sherman's vulnerability. German Panzer IV tanks initially stored ammunition in the hull sponsons similar to American practice, though later variants incorporated some additional protection measures. The Panther tank, rushed into production during 1943 to counter the T-34, stored significant ammunition quantities in the hull sides, where penetrating hits from Soviet anti-tank guns could easily reach them. Every nation fielding tanks in World War II struggled with the fundamental tension between ammunition capacity, crew accessibility, internal volume constraints, and protection against post-penetration fires. The difference emerged in how aggressively each nation's ordnance establishment worked to address the problem and how quickly solutions reached combat units. American ordnance engineers at Aberdeen Proving Ground in Maryland had been studying tank ammunition fire hazards since early 1942, even before combat reports from North Africa confirmed the severity of the problem. Initial research focused on understanding the thermal and mechanical mechanisms that caused sympathetic detonation when one propellant case ignited adjacent cases in a rapid cascade. High-speed photography of controlled ammunition fires revealed that propellant ignition generated intense heat that rapidly raised the temperature of neighboring shells above their ignition point, typically around 190 degrees Celsius for the propellant compounds used in American tank ammunition. Once this cascade began, nothing could stop it. The entire ammunition load would cook off in sequence, generating temperatures and pressures that buckled armor plate from the inside and expelled turrets from their rings. Engineers tested various protection concepts through 1942 and into 1943. Simply increasing armor thickness around ammunition bins would add unacceptable weight, relocating all ammunition to the turret bustle, as the British experimented with on some designs, severely limited ammunition capacity and created its own vulnerability if the bustle was struck. The solution that emerged from systematic testing involved a deceptively simple principle. If propellant could be prevented from reaching ignition temperature despite exposure to heat from an initial fire, the sympathetic detonation cascade could be interrupted. The method Aberdeen engineers developed used liquid coolant surrounding each propellant case to absorb thermal energy and maintain temperatures below the ignition point long enough for automatic fire suppression systems to activate or crews to manually extinguish flames. The specific liquid chosen was a mixture of water and ethylene glycol in varying proportions depending on the design iteration. Early tests used pure water, which proved highly effective at thermal absorption but froze in cold weather and caused corrosion problems in steel ammunition containers. The addition of ethylene glycol, the same antifreeze compound used in automotive cooling systems, prevented freezing while maintaining excellent thermal absorption properties. The final production mixture settled on approximately 40% ethylene glycol and 60% water by volume, though some units in the field reported variations in this ratio. This solution, dubbed wet storage or wet stowage in official documentation, surrounded each 75mm or 76mm propellant case in a sealed jacket that held approximately half a litre of liquid coolant. Testing at Aberdeen Proving Ground demonstrated dramatic improvements in fire resistance. Ammunition stored in wet stowage containers survived direct flame exposure for up to 3 to 5 minutes before igniting, compared to less than 30 seconds for dry stored ammunition under identical conditions. This extra time proved critical in combat situations. It allowed automatic fire extinguishers to function, gave crews time to activate manual suppression systems, or provided those crucial extra seconds for evacuation if the fire could not be controlled. The wet stowage system added approximately 227 kilograms of weight to the tank, including the liquid coolant, reinforced containers, and associated plumbing for drainage and maintenance. This weight penalty was considered acceptable, given the substantial improvement in crew survivability. The redesign required more than just adding liquid containers around existing ammunition racks. The entire internal layout of the Sherman hull needed modification to accommodate wet stowage bins while maintaining loader efficiency and crew mobility. The solution relocated most hull ammunition from the vulnerable sponson positions to bins mounted on the floor of the fighting compartment beneath the turret basket. This floor-mounted placement offered several advantages. It positioned ammunition lower in the hull, where penetrating hits were less likely to reach, placed ammunition behind the thickest armor sections where glacis plate angles provided maximum protection, and created separation between the crew fighting positions and the ammunition, reducing blast effects if detonation did occur despite the wet stowage protection. The floor-mounted bins featured hinged covers that the loader could access without leaving his position, maintaining operational efficiency during sustained firing. Each bin contained individual water jackets that could be removed for maintenance or replaced if damaged. The system included drainage ports to empty liquid coolant for winter storage or when operating in extreme cold, though doctrine emphasized keeping the system filled whenever possible for maximum protection. Spring-loaded clips held each round securely in place to prevent shifting during movement, while allowing quick extraction when needed. The engineering was sophisticated in execution, but elegantly simple in concept, reflecting American ordnance philosophy that prioritized practical functionality and field maintainability over theoretical optimization. Production of wet storage. Shermans began in February 1944 at multiple manufacturing facilities. Chrysler Defense Arsenal in Detroit, Fisher Tank Arsenal in Grand Blanc, Michigan, Federal Machine and Welder in Warren, Ohio, and other manufacturers simultaneously retooled assembly lines to accommodate the new internal configuration. The conversion required approximately 6 weeks to implement at each facility, during which production rates dropped by roughly 15% as workers adapted to new procedures and tooling. By April 1944, all new Sherman production incorporated wet stowage as standard equipment. The timing, though it appeared deliberate, actually reflected the extended period required for any major design change to progress from testing through approval, manufacturing preparation, and final implementation across multiple factories. The first wet storage Shermans reached Britain in May 1944, arriving too late for initial deployment during the Normandy landings on June 6. The Supreme Headquarters Allied Expeditionary Force had not specifically requested priority delivery of wet storage tanks for the invasion, partly because senior commanders remained unaware of the modification's significance, and partly because logistics planning for Operation Overlord had been finalized months earlier, using existing equipment inventories. Consequently, American armored divisions that stormed the Normandy beaches fought with older dry storage, Shermans that retained the ammunition fire vulnerability that would cost numerous lives over the coming weeks. This timing failure would later be recognized as a significant missed opportunity to improve crew survivability during the difficult hedgerow fighting, where German anti-tank guns achieved numerous close-range penetrations. The Normandy campaign from June through August 1944 demonstrated with brutal clarity the tactical consequences of ammunition fire vulnerability. German defensive doctrine in the bocage terrain of Normandy emphasized ambush tactics using towed 75mm and 88mm anti-tank guns positioned to cover the limited approach routes through hedgerow-lined lanes. These guns, expertly camouflaged and supported by infantry with Panzerfaust anti-tank rockets, engaged American armor at ranges where penetration was virtually guaranteed. British and American tank battalions reported devastatingly high loss rates, with entire companies sometimes reduced to a handful of operational vehicles after a single day's fighting. Post-battle analysis of destroyed tanks found that the vast majority had burned completely, often with fatal consequences for crews who could not evacuate before flames blocked hatches or generated lethal temperatures inside fighting compartments. Lieutenant Colonel Creighton Abrams, commanding the 37th Tank Battalion of the 4th Armoured Division, personally observed multiple instances where his Shermans burned after penetrating hits that might otherwise have resulted in repairable damage. Abrams, who would later rise to become United States Army Chief of Staff, understood viscerally that crew survival depended not just on avoiding penetration, which was often impossible against well-positioned German guns, but on preventing secondary fires that turned mobility kills into crew deaths. His battalion, like most American armor units in Normandy, fought with dry storage, Shermans through July and into August, suffering casualties that might have been reduced had wet storage tanks been available earlier. The technical specifications of wet stowage protection became clear through systematic testing, even as combat experience accumulated in France. Aberdeen Proving Ground conducted extensive trials throughout spring and summer 1944, measuring precisely how much additional protection the liquid coolant provided under various combat scenarios. Engineers fired 88mm armor-piercing rounds into wet storage, Shermans at controlled angles and velocities, then documented fire development and ammunition detonation timing. The results quantified what field observations would later confirm. Wet storage reduced catastrophic ammunition fire rates from approximately 60 to 80% of penetrating hits down to approximately 10 to 15% under comparable circumstances. The improvement was not absolute. Wet storage could not prevent ammunition fires in all circumstances, particularly when multiple penetrations occurred in rapid succession or when high explosive shells detonated inside ammunition compartments, rupturing water jackets and igniting propellant directly. But the significant reduction in fire frequency translated directly into improved crew survivability. Tank crews struck by armor-piercing rounds in wet storage, Shermans had substantially better chances of evacuating safely or even continuing to fight if the penetration disabled systems without causing immediate fire. German intelligence officers examining knocked-out American tanks in Normandy during July 1944 began noticing destroyed Shermans that had been penetrated, but showed no evidence of extensive internal fire damage. This observation appeared in intelligence reports circulated to panzer units, though initial analysis attributed the phenomenon to American crews more rapidly evacuating after penetration rather than to any design modification. Not until August, when German recovery teams salvaged several disabled but relatively intact Shermans from contested battlefields, did German technical intelligence recognize that American engineers had implemented a significant internal modification specifically designed to prevent ammunition fires. The discovery troubled German ordnance officials who understood its implications. If American industry could respond to a known vulnerability by developing, testing, and fielding a comprehensive solution within approximately 18 months from problem identification to combat deployment, while simultaneously maintaining tank production rates exceeding German output by factors of 5 to 1 or greater, the cumulative advantage in both quantity and improving quality rendered German tactical superiority increasingly irrelevant. Germany possessed highly capable tank designs, better crew training in many respects, and superior tactical doctrine in defensive operations, but could not match American industrial capacity to identify problems and implement solutions at scale while fighting on multiple fronts. The German Panther tank, by comparison, had been rushed into combat during summer 1943 at Kursk, despite serious reliability problems that should have delayed deployment. Final drive failures, engine fires, transmission breakdowns, and numerous other mechanical issues plagued Panthers throughout 1943 and into 1944. German ordnance engineers identified these problems through field reports and testing, but lacked the industrial capacity to implement comprehensive corrections while maintaining production rates. Incremental improvements gradually addressed the worst reliability issues, but Panthers never achieved the mechanical dependability that American Shermans demonstrated from initial production. Now German intelligence was documenting that American engineers had simultaneously solved a survivability problem that German designers had largely ignored while focusing on armor thickness and gunpowder. Reports from panzer commanders in France noted with concern that knocked-out American tanks were increasingly being recovered and returned to service by American maintenance units. Previously, Penetrated Shermans typically burned so completely that recovery was pointless, the hulls too damaged for economical repair. Wet storage Shermans that survived penetration without catastrophic fires could often be evacuated from battlefields, repaired at field maintenance facilities, and returned to combat within days or weeks. This recovery and repair capability multiplied American numerical advantages, allowing damaged tanks to rejoin combat units multiple times throughout the campaign, while German tanks, once knocked out, were frequently lost permanently due to inability to recover them before American advances overran positions. The first comprehensive American analysis of wet storage effectiveness in combat came from the European Theatre of Operations Operational Research Section, a specialized unit that systematically examined tank losses to identify patterns and recommend improvements. The research team, composed of civilian statisticians, engineers, and military officers, conducted detailed examinations of destroyed tanks throughout France during late summer and autumn 1944. Their methodology was rigorous. Each destroyed Sherman was photographed, measured, and analyzed to determine the cause of loss, location of penetrating hits, extent of fire damage, and crew casualties. The data accumulated from hundreds of individual tank examinations provided the first statistically valid evidence of wet storage effectiveness under actual combat conditions. The preliminary report, circulated in September 1944, documented a striking correlation between ammunition storage type and crew survival rates. Shermans with dry storage that suffered penetrating hits to ammunition compartments experienced catastrophic fires in approximately 60% of cases, with crew fatalities averaging 3.2 per tank when fires occurred. Wet storage Shermans suffering comparable penetrations experienced catastrophic fires in only 15% of cases, with crew fatalities averaging 1.1 per tank when fires did occur. The difference was statistically significant beyond any reasonable doubt and represented one of the most important survivability improvements implemented during the entire war. The report's findings reached senior American commanders in October 1944, generating immediate demands for accelerated delivery of wet storage tanks to frontline units. General Omar Bradley, commanding the 12th Army Group, personally reviewed the casualty data and recognized that thousands of American faces by the date. Tank crewmen had died in fires that wet storage might have prevented. Bradley immediately contacted the War Department, requesting confirmation that all Sherman production now incorporated wet storage and demanding that existing dry storage tanks in rear areas be replaced with wet storage variants as rapidly as possible. The response confirmed that production had converted completely to wet storage by April 1944, but substantial numbers of dry storage tanks remained in service, with units that had deployed to Europe before the new variants arrived in quantity. The logistical challenge of replacing dry storage tanks with wet storage variants while maintaining combat operations proved substantial. American armored divisions operated with authorized strengths of approximately 200 medium tanks distributed across 3 tank battalions and supporting units. Replacing every dry storage, Sherman would require delivering 200 new tanks per division, while simultaneously evacuating 200 old tanks for rear echelon use or return to the United States. The shipping capacity for such a replacement program did not exist given competing priorities for transporting ammunition, fuel, spare parts, and replacement personnel. Instead, ordnance officers developed a phased replacement strategy where dry storage tanks were withdrawn from combat units only when they required major maintenance or suffered combat damage requiring depot-level repair. Wet storage tanks arriving from the United States or Britain replaced these withdrawn vehicles, gradually converting the fleet without disrupting combat operations. By November 1944, approximately 60% of American Sherman tanks in frontline combat units incorporated wet storage. The remaining 40% were gradually replaced over subsequent months, as the replacement pipeline delivered new production and combat losses were made good with wet storage variants. This gradual transition meant that American tank battalions through the winter of 1944 to 45 typically operated with mixed fleets, some crews fighting in wet storage Shermans while others remained in older dry storage variants. The disparity created morale problems when crews learned that some tanks offered significantly better fire protection than others. Commanders attempted to assign wet storage tanks based on tactical considerations, giving them to platoons expected to face the heaviest opposition, but this proved difficult in fluid combat situations where enemy contact occurred unpredictably. The Battle of the Bulge, beginning December 16, 1944, provided another intensive test of wet storage effectiveness under severe winter combat conditions. German forces, launching their surprise offensive through the Ardennes, achieved tactical surprise and local superiority, ambushing American units and destroying substantial numbers of tanks in the opening days. The bitter cold, with temperatures dropping below -10 degrees Celsius, raised concerns about whether wet storage coolant would freeze despite the ethylene glycol antifreeze, potentially reducing protection effectiveness. Field reports from units engaged in the desperate fighting documented that wet storage continued functioning effectively in extreme cold, though some crews reported that coolant had partially frozen in tanks left immobile overnight in unheated positions. Doctrine emphasized that tanks should be started and run periodically, even when not actively engaged, to maintain engine temperature and prevent coolant freezing. But combat conditions often prevented this maintenance procedure. American tank losses during the Bulge were substantial, with some units reporting 50% or higher casualties in vehicles and crews during the first week of fighting. German forces deployed significant numbers of Panther and Tiger tanks, supported by assault guns and towed anti-tank weapons, all engaging American armor at close range in heavily wooded terrain that negated American advantages in air support and long-range observation. The casualty analysis conducted after the battle revealed that wet storage Shermans continued demonstrating significantly lower fire rates than dry storage tanks under identical combat circumstances. The data suggested that wet storage effectiveness was not substantially degraded by cold weather, heavy combat intensity, or multiple penetrations in rapid succession, though absolute protection could never be guaranteed under worst-case scenarios. Lieutenant James Burt of the 66th Armored Regiment documented one particularly striking example of wet storage effectiveness during fighting near Butgenbach in late December. His Sherman, a wet storage M4A1, was struck twice by German anti-tank fire within a 30-second period. The first round penetrated the right sponson, passing completely through the hull without striking ammunition. The second round, fired from a different angle, penetrated the lower hull and struck the floor-mounted ammunition bins directly. Burt's crew braced for the explosion they had seen consume other tanks, but the wet storage containers absorbed the thermal energy from the penetrating round without igniting. The tank was immobilized by damage to the transmission and final drive, but the crew evacuated safely without injuries. Burt specifically mentioned in his after-action report that he believed wet storage had saved his crew's lives, and he personally wrote a letter to ordnance officials at Aberdeen Proving Ground thanking them for the modification. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German examination of captured wet storage Shermans during the Bulge offensive provided the first detailed technical intelligence on the system's design and function. A nearly intact M4, a 3 wet storage, Sherman captured near Bastogne on December 23rd, was transported to a rear area collection point for systematic analysis. German engineers photographed the ammunition storage system, measured the water jacket dimensions, and analyzed the coolant composition through chemical testing. Their report, distributed to Heereswaffenamt officials in January 1945, acknowledged that the American solution was elegantly simple and highly effective within its design parameters. The report noted that implementing a comparable system in German tanks would require substantial redesign of internal layouts, modifications to ammunition packaging, and additional weight that Panther and Tiger designs could not accommodate without performance degradation. More troubling to German analysts was the implicit evidence that American industrial capacity could respond to identified vulnerabilities faster than German forces could exploit them tactically. The timeline from problem identification through solution development and fleet-wide implementation had taken American ordnance approximately 18 to 24 months, a remarkably short period for a modification requiring complete internal redesign and manufacturing retooling across multiple factories. German tank development, by comparison, required years to progress from concept through testing to production, with the Panther taking approximately 3 years from initial specification to combat deployment and still entering service with serious unresolved reliability problems. The contrast highlighted fundamental differences in industrial maturity, organizational efficiency, and engineering philosophy that favored American approaches despite German theoretical advantages in some technical areas. The psychological impact on German tank crews of facing increasingly capable American armor should not be underestimated. Throughout 1943 and into early 1944, German tankers had maintained psychological advantage derived from knowing their vehicles possessed superior armor protection and firepower compared to most Allied tanks. Panthers could destroy Shermans from ranges where return fire was ineffective. Tigers were nearly invulnerable to frontal attack from standard Allied weapons. This technical superiority provided confidence that partially compensated for American numerical advantages and air superiority. By late 1944, this confidence had eroded significantly. American tanks now carried HVAP ammunition that could penetrate Panther mantlets at combat ranges. American crews demonstrated increasing tactical competence developed through sustained combat experience. American recovery and repair capabilities meant that knocked-out Shermans frequently returned to combat, while German tanks, once disabled, were usually lost permanently. The knowledge that American tanks also incorporated protection systems that allowed crews to survive hits that would have been fatal in earlier variants added to the erosion of German psychological advantage. Panther and Tiger crews understood that their armor offered protection, but that single good hit could still destroy their vehicle if ammunition was struck or fuel tanks ruptured. German tanks had no equivalent wet storage protection, relying instead on armor thickness to prevent penetration entirely. This all-or-nothing approach worked when German tanks could engage from favorable positions at long range, but broke down when forced into close-range engagements, where American numerical superiority and combined arms tactics negated German advantages. The result was increasing German caution and defensive mentality that surrendered tactical initiative to American forces who exploited this psychological shift ruthlessly. Soviet forces operating Sherman tanks through the Lend-Lease program also benefited from wet storage protection, though Soviet combat doctrine and tactical methods differed substantially from American practice. The Soviet Union received approximately 4,000 Sherman tanks during the war, primarily M4A, 2 variants with diesel engines preferred by Soviet maintenance personnel. These tanks served in Guards tank brigades and other elite formations where mechanical reliability and logistics were better than average for Soviet armored units. Soviet after-action reports rarely documented casualty details with the precision American reports maintained, making statistical analysis of wet storage effectiveness in Soviet service difficult. However, Soviet tank commanders interviewed after the war consistently praised the Sherman's survivability compared to Soviet-built T-34 tanks, which remained highly vulnerable to catastrophic ammunition fires throughout the war, despite several design iterations. The T-34's ammunition storage, scattered throughout the fighting compartment with minimal protection, created severe vulnerability to penetrating hits from German anti-tank weapons. Soviet crews nicknamed disabled T-34 seconds that burned with their entire crew trapped inside as coffins, a grimly accurate description of the fate that awaited crews who could not evacuate before fire blocked hatches. German tank commanders on the Eastern Front explicitly trained their gunners to target T-34 hull shots because penetrations almost invariably resulted in catastrophic fires. The contrast between T-34 vulnerability and Sherman survivability, particularly wet storage variants, influenced Soviet post-war tank design philosophy. The T-54 and subsequent Soviet tank designs incorporated improved ammunition protection, including partial liquid cooling systems, clearly influenced by examination of Lend-Lease Sherman wet storage designs. The production statistics for wet storage Shermans reveal the scale of American industrial response to the survivability problem. From February 1944 through the end of production in 1945, American factories manufactured approximately 30,000 wet storage Shermans of all variants. This represented roughly 60% of total Sherman production during this period, with the remaining 40% being specialized variants like the M4A3E2 assault tank or vehicles produced for specific Lend-Lease requirements that did not incorporate wet storage. The conversion from dry storage to wet storage production occurred simultaneously across 11 different manufacturing facilities operated by 6 different companies, requiring coordination of design changes, tooling modifications, and supply chain adjustments across the entire industrial base. The fact that this conversion occurred with minimal disruption to production schedules, while factories were simultaneously increasing output to meet growing combat requirements, demonstrated organizational and industrial capabilities that no other combatant nation could match. German tank production, by comparison, struggled to maintain output above 400 vehicles per month through 1944, despite desperate need for replacement vehicles. Allied strategic bombing targeted key bottlenecks in German production, including the Maybach engine plant at Friedrichshafen and the ZF transmission facility, causing severe disruptions. Slave labor, increasingly employed in German factories as German workers were conscripted for military service, introduced quality problems and deliberate sabotage that affected reliability. Raw material shortages forced substitution of inferior steel alloys in critical components, reducing service life and increasing failure rates. The German industrial system was collapsing under accumulated strain even as American production accelerated and incorporated continuous improvements like wet storage that enhanced effectiveness without reducing output. The comparative effectiveness of American versus German approaches to tank survivability extended beyond ammunition protection to fundamental design philosophy differences. German tanks emphasized armor thickness and weapon power to prevent penetration entirely, accepting weight increases and mechanical complexity as necessary costs. When this approach worked, German tanks dominated engagements through superior firepower and protection. When it failed, either through mechanical breakdown or penetration by increasingly capable Allied weapons, German tanks and crews were lost with little chance of recovery. American tanks emphasized automotive reliability, ease of repair, and crew survivability through multiple overlapping systems, including wet storage, escape hatches, fire suppression, and internal layout designed to isolate crew from ammunition. This approach accepted that tanks would be penetrated in combat, but designed to maximize crew survival and vehicle recoverability when penetration occurred. The statistical evidence accumulated through 1945 conclusively validated American philosophy. Tank for tank, the Sherman was inferior to the Panther in armor protection and firepower. Crew for crew, experienced American tankers were roughly equal to experienced German tankers in tactical competence, though German crews averaged more training. Yet American armored forces consistently achieved favorable operational outcomes through superior logistics, overwhelming numerical advantage, complete air superiority, and significantly better crew survival rates that preserved experienced personnel. Wet storage contributed materially to this survival advantage, keeping crews alive through engagements that would have killed them in earlier tanks, allowing them to accumulate experience and develop the tactical competence that made American armor increasingly effective as the war progressed. The British Army's experience with wet storage Shermans provides additional perspective on the modification's effectiveness across different tactical doctrines and operational contexts. British armoured regiments received wet storage Shermans beginning in summer 1944, with priority going to units preparing for Operation Market Garden in September and subsequent operations in Holland and Germany. British doctrine emphasised different tactical approaches than American practice, with British units more willing to accept casualties to achieve breakthrough objectives and less concerned with crew survivability as an independent metric. Despite these doctrinal differences, British after-action reports documented similar patterns to American experience. Wet storage Shermans demonstrated substantially lower fire rates after penetration compared to dry storage variants, with corresponding improvements in crew survival and vehicle recovery rates. British crews, like their American counterparts, quickly recognized the survivability advantages wet storage provided and actively preferred assignment to wet storage tanks when available. The British nickname for the Sherman, the Ronson lighter, gradually fell out of common use as wet storage variants became predominant, replaced by more neutral terminology that reflected reduced fire vulnerability. This linguistic shift, though seemingly trivial, indicated changed perception based on operational experience. When Shermans burned regularly after penetration, crews developed gallows humor about it. When they stopped burning as frequently, the humor became unnecessary and disappeared naturally from unit culture. The engineering sophistication of wet storage becomes more apparent when examining the detailed design decisions that made the system practical for field service. The water jackets surrounding each propellant case needed to be robust enough to survive rough handling during ammunition loading and transportation, yet light enough to avoid excessive weight penalties. The containers needed to seal completely to prevent coolant leakage, yet allow easy access for routine maintenance and coolant replacement. The internal mounting system needed to hold ammunition securely during violent maneuvering and weapons firing, yet release rounds smoothly when the loader pulled them for loading. Each of these requirements presented engineering challenges that Aberdeen Proving Ground designers solved through iterative testing and refinement. The water jacket material was stamped steel approximately 1 mm thick, formed into containers that enclosed the propellant case, while leaving the projectile exposed for loader visibility and handling. Each jacket held approximately 450 milliliters of coolant solution, precisely calculated to provide adequate thermal absorption capacity without adding unnecessary weight. The jacket sealing method used rolled seams crimped under pressure, creating liquid-tight closure without requiring welding that might introduce heat distortion or weak points. The mounting brackets holding jackets in floor-mounted bins featured spring-loaded clips that gripped jacket flanges with sufficient force to prevent shifting during movement, yet released cleanly when the loader pulled upward on the projectile. The entire system reflected careful attention to practical details that separated functional equipment from laboratory concepts that worked under controlled conditions but failed in field service. Maintenance requirements for wet storage added modest additional workload to crew and maintenance personnel duties. Technical manuals specified that coolant levels should be checked weekly when in combat zone and replenished as necessary to maintain design levels. The coolant solution did not degrade significantly over time, so complete replacement was only necessary if contamination occurred or if the system had been drained for winter storage. Leaking water jackets, damaged by rough handling or combat-related stress, needed replacement to maintain protection effectiveness. The logistics system provided replacement water jackets through normal parts supply channels, classified as high-priority items due to their direct impact on crew survivability. Field maintenance companies kept stocks of water jackets and coolant solution, allowing rapid replacement when needed. Combat damage sometimes ruptured water jackets, even when ammunition did not ignite, requiring careful inspection after engagement to identify compromised containers. Crews were instructed to check for coolant puddles in ammunition compartments after receiving penetrating hits or near misses that might have caused internal damage. Ruptured jackets were removed and replaced immediately, with the affected ammunition round still usable, though no longer protected. This maintenance procedure, though adding workload, became routine for experienced crews, who understood that properly functioning wet storage directly affected their survival probability. The expansion of wet storage technology to other ammunition types demonstrated American Ordnance Establishment willingness to apply proven solutions broadly across multiple weapon systems. The 76mm gun that armed later Sherman variants used longer, more powerful ammunition that required different water jacket designs. Engineers at Aberdeen developed scaled-up versions of the original 75mm jackets, maintaining the same coolant mixture and thermal protection principles, while accommodating the larger propellant cases. These 76mm wet storage systems entered production in mid-1944, reaching units simultaneously with the guns themselves. The coordination ensured that crews receiving improved armament also received improved protection without lag time between deployments. Tank destroyer units operating M10 and M18 vehicles, armed with 76mm guns, also received wet storage ammunition as it became available. The M36 tank destroyer, mounting a 90mm gun, used yet another variant of the wet storage system specifically designed for the substantially larger propellant cases required by the more powerful weapon. By early 1945, American doctrine specified that all armored fighting vehicles carrying ammunition in quantities sufficient to create catastrophic fire hazards should incorporate wet storage or equivalent protection as standard equipment. This policy, driven by accumulated evidence of effectiveness, ensured that future American tank designs would include comprehensive ammunition, fire protection from initial specification, rather than adding it as a retrofit after problems emerged in combat. The post-war analysis of tank crew casualties provided definitive statistical validation of wet storage effectiveness measured against the ultimate metric of lives saved. The United States Army Historical Section conducted comprehensive studies examining tank crew casualties throughout the European campaign, correlating casualty rates with tank types, ammunition storage configurations, and combat circumstances. The final report, completed in 1947 after years of detailed analysis, concluded that wet storage reduced tank crew fatalities by approximately 40 to 50% compared to dry storage under comparable combat conditions. This represented one of the single most effective survivability improvements implemented during the entire war, measured by lives directly saved through the modification. The human cost of the delay in implementing wet storage troubled some post-war analysts who calculated that thousands of American tank crewmen died in fires that might have been prevented had wet storage reached combat units sooner. The modification was technically feasible by mid-1943 based on Aberdeen Proving Ground testing, but production implementation required manufacturing preparation, quality validation, and logistics coordination that consumed 6 to 9 months before the first wet storage tanks reached combat units. An additional 6 to 9 months elapsed before wet storage tanks constituted the majority of deployed vehicles. During this 18-month period from technical feasibility to fleet conversion, American armored forces fought in Sicily, Italy, and Normandy, with dry storage tanks that killed their crews when penetrated. Whether this delay was unavoidable given the complexity of coordinating major design changes across multiple factories during wartime, or whether it represented bureaucratic failure to prioritize a known life-saving modification, remained subject to debate among historians examining the decision-making process. The consensus view held that ordnance officials acted as quickly as reasonably possible, given competing priorities and limited information about the severity of the problem before substantial combat data accumulated from North Africa and Italy. Nonetheless, the human cost of fighting without optimal survivability equipment remained a sobering reminder of how design and production timelines measured in months translated into casualties measured in thousands of lives. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.